directed, strike the turbine blades, arranged radially around the outer edge of the turbine, and cause the rotor, turbine and impeller to rotate. The gases, having exhausted most of their energy, are then exhausted overboard. When the wastegate is fully open, nearly all of the exhaust gases pass overboard, providing little or no boost. Normalizer turbocharger. Some engines used in light aircraft are equipped with an externally driven normalizing system. These systems are powered by the energy of exhaust gases and are usually referred to as normalizing turbocharger systems. These systems were not designed to be used as a true supercharger boost manifold pressure over 30 Hg. They compensate for the power lost due to the pressure drop resulting from increased altitude. On many small aircraft engines, the turbocharger normalizing system is designed to be operated only above a certain altitude, 5,000 feet for example, since maximum power without normalizing is available below that altitude. The location of the air induction and exhaust systems of a typical normalizing turbocharger system for a small aircraft is shown in Figure 3-16. Ground-boosted turbo-supercharger system. Some ground-boosted, sea-level, turbo-supercharged systems are designed to operate from sea level up to their critical altitude. These engines, sometimes referred to as sea-level boosted engines, can develop more power at sea level than an engine without turbo-supercharging. As was mentioned earlier, an engine must be boosted above 30 Hg to truly be supercharged. This type of turbocharger accomplishes this by increasing the manifold pressure above 30 Hg to around 40 Hg. The turbo-supercharger air induction system consists of a filtered ram air intake located on the side of the nacelle. Figure 3-17. An alternate air door within the nacelle permits compressor suction automatically to admit alternate air, heated engine compartment air, if the induction air filter becomes clogged. In many cases, the alternate air door can be operated manually in the event of filter clogging. Almost all turbocharger systems use engine oil as the control fluid for controlling the amount of boost, extra manifold pressure, provided to the engine. The wastegate actuator and controllers use pressurized engine oil for their power supply. The turbocharger is controlled by the wastegate and wastegate actuator. The wastegate actuator, which is physically connected to the wastegate by mechanical linkage, controls the position of the wastegate butterfly valve. The wastegate bypasses the engine exhaust gases around the turbocharger turbine inlet. By controlling the amount of exhaust gases, throttle and mixture control, control system, exhaust system, intake manifold, air intake alternate air intake turbocharger, induction system. Figure 3-16. Typical location of the air induction and exhaust systems of a normalizing turbocharger system. 3-11. Induction system balance tube. Code. Ram air ram filtered air compressed air heated air. Mechanical linkage oil pressure oil return. Induction manifold left hand bank. Filtered ram air. Induction manifold right hand bank. Turbocharger. Throttle body alternate air door, normally closed. Wastegate controller. Filter. Wastegate actuator. Wastegate. Induction system balance tube. Induction manifold left hand bank. Induction manifold right hand bank. Heated air. Turbocharger. Throttle body alternate air door, open. Wastegate controller. Filter. Wastegate actuator. Wastegate. Figure 3-17. A turbocharger air induction system that pass through the turbine of the turbocharger, the speed of the compressor and the amount of intake boost, upper deck pressure, is controlled. Engine oil is also used to cool and lubricate the bearings that support the compressor and turbine in the turbocharger. Turbocharger lubricating oil is engine oil supplied through the engine oil system. An oil supply hose from the rear of the oil cooler directs oil to the turbocharger center housings and bearings. Oil hoses return oil from the turbochargers to the oil scavenge pump located on the rear of the engine. The one-way check valve in the oil supply line prevents oil from draining into the turbocharger while the engine is not operating. Piston ring-like oil seals are 3-12. Used on the compressor wheel shaft to prevent the lubricating oil from entering the turbine and compressor housings from the center housing. The position of the wastegate is controlled by adjusting the oil pressure in the wastegate actuator. Several different types of controllers are used to provide the correct pressure in the wastegate actuator. This is done either by restricting the oil flow or by allowing the oil to return to the engine. The more the oil is restricted, the more pressure is in the wastegate actuator, and the more closed the wastegate is. This causes the exhaust gases to pass through the turbine, increasing the speed of the compressor, raising the inlet pressure. The reverse happens if the oil is not restricted by the controllers and boost is reduced. The pressure from the outlet of the compressor of the turbocharger to the throttle is referred to as deck pressure or upper deck pressure. A typical turbo-supercharger system. Figure 3-18 is a schematic of a sea-level booster turbo-supercharger system. This system used widely is automatically regulated by three components: exhaust bypass valve assembly, density controller, differential pressure controller. By regulating the wastegate position and the fully open and closed positions, a constant power output can be maintained. When the wastegate is fully open, all the exhaust gases are directed overboard to the atmosphere, and no air is compressed and delivered to the engine air inlet. Conversely, when the wastegate is fully closed, a maximum volume of exhaust gases flows into the turbocharger turbine, and maximum supercharging is accomplished. Between these two extremes of wastegate position, constant power output can be achieved below the maximum altitude at which the system is designed to operate. An engine with a critical altitude of 16,000 feet cannot produce 100% of its rated manifold pressure above 16,000 feet. Critical altitude means the maximum altitude at which, in standard atmosphere, it is possible to maintain, at a specified rotational speed, a specified power, or a specified manifold pressure. Oil return to crankcase, turbocharger exhaust gas discharge, exhaust manifold, differential pressure control, engine oil pressure inlet, fuel injector density controller. Oil return to crankcase, exhaust bypass valve assembly, exhaust gases compressor discharge pressure inlet manifold pressure. Oil, air oil exhaust gas, filter air inlet. Figure 3-18. Sea level booster turbo supercharger system. 3-13. A critical altitude exists for every possible power setting below the maximum operating ceiling. If the aircraft is flown above this altitude without a corresponding change in the power setting, the wastegate is automatically driven to the fully closed position in an effort to maintain a constant power output. Thus, the wastegate is almost fully open at sea level, and continues to move toward the closed position as the aircraft climbs, in order to maintain the pre-selected manifold pressure setting. When the wastegate is fully closed, leaving only a small clearance to prevent sticking, the manifold pressure begins to drop if the aircraft continues to climb. If a higher power setting cannot be selected, the turbocharger's critical altitude has been reached. Beyond this altitude, the power output continues to decrease. The position of the wastegate valve, which determines power output, is controlled by oil pressure. Engine oil pressure acts on a piston in the wastegate assembly, which is connected by linkage to the wastegate valve. When oil pressure is increased on the piston, the wastegate valve moves toward the closed position, and engine output power increases. Conversely, when the oil pressure is decreased, the wastegate valve moves toward the open position, and output power is decreased as described earlier. The position of the piston attached to the wastegate valve is dependent on bleed oil, which controls the engine oil pressure applied to the top of the piston. Oil is returned to the engine crankcase through two control devices, the density controller and the differential pressure controller. These two controllers, acting independently, determine how much oil is bled back to the crankcase and establishes the oil pressure on the piston. The density controller is designed to limit the manifold pressure below the turbocharger's critical altitude and regulates bleed oil only at the full throttle position. The pressure and temperature sensing bellows of the density controller react to pressure and temperature changes between the fuel injector inlet and the turbocharger compressor. The bellows, filled with dry nitrogen, maintain a constant density by allowing the pressure to increase as the temperature increases. Movement of the bellows repositions the bleed valve, causing a change in the quantity of bleed oil, which changes the oil pressure on top of the wastegate piston. Figure 3-18. The differential pressure controller functions during all positions of the wastegate valve other than the fully open position, which is controlled by the density controller. One side of the diaphragm in the differential pressure controller senses air pressure upstream from the throttle. The other side samples pressure on the cylinder side of the throttle valve. Figure 3-18. At the wide open throttle position when the density controller controls the wastegate, the pressure across the differential pressure controller diaphragm is at a minimum and the controller spring holds the bleed valve closed. At part throttle position, the air differential is increased, opening the bleed valve to bleed oil to the engine crankcase and reposition the wastegate piston. Thus, the two controllers operate independently to control turbocharger operation at all positions of the throttle. Without the overriding function of the differential pressure controller during part throttle operation, the density controller would position the wastegate valve for maximum power. The differential pressure controller reduces injector entrance pressure, and continually repositions the valve over the whole operating range of the engine. The differential pressure controller reduces the unstable condition known as bootstrapping during part throttle operation. Bootstrapping is an indication of unregulated power change that results in the continual drift of manifold pressure. This condition can be illustrated by considering the operation of a system when the wastegate is fully closed. During this time, the differential pressure controller is not modulating the wastegate valve position. Any slight change in power caused by a change in temperature or RPM fluctuation is magnified and results in manifold pressure change since the slight change causes a change in the amount of exhaust gas flowing to the turbine. Any change in exhaust gas flow to the turbine causes a change in power output and is reflected in manifold pressure indications. Bootstrapping, then, is an undesirable cycle of turbocharging events causing the manifold pressure to drift in an attempt to reach a state of equilibrium. Bootstrapping is sometimes confused with a condition known as overboost. But bootstrapping is not a condition that is detrimental to engine life. An overboost condition is one in which manifold pressure exceeds the limits prescribed for a particular engine, and can cause serious damage. A pressure relief valve when used in some systems, set slightly in excess of maximum deck pressure, is provided to prevent damaging overboost in the event of a system malfunction. The differential pressure controller is essential to smooth functioning of the automatically controlled turbocharger, since it reduces bootstrapping by reducing the time required to bring a system into equilibrium. There is still extra throttle sensitivity with a turbocharged engine than with a naturally aspirated engine. Rapid movement of the throttle can cause a certain amount of manifold pressure drift in a turbocharged engine. Less severe than bootstrapping. This condition is called overshoot. While overshoot is not a dangerous condition, it can be a source of concern to the pilot or operator who selects a particular manifold pressure setting only to find it has changed in a few seconds and must be reset. Since the automatic controls cannot respond rapidly enough to abrupt changes in throttle settings to eliminate the 3-14 inertia of turbocharger speed changes, overshoot must be controlled by the operator. This can best be accomplished by slowly making changes in throttle setting, accompanied by a few seconds wait for the system to reach a new equilibrium. Such a procedure is effective with turbocharged engines, regardless of the degree of throttle sensitivity. Turbocharger controllers and system descriptions. Turbocharger system engines contain many of the same components mentioned with the previous systems. Figure 3-19. Some systems use special lines and fittings that are connected to the upper deck pressure for air reference to the fuel injection system, and in some cases for pressurizing the magnetos. Basic system operation is similar to other turbocharger systems, with the main differences being in the controllers. The controller monitors deck pressure by sensing the output of the compressor. The controller controls the oil flow through the waste ticket actuator, which opens or closes the exhaust bypass valve. When deck pressure is insufficient, the controller restricts oil flow, thereby increasing oil pressure at the waste ticket actuator. This pressure acts on the piston to close off the waste ticket valve, forcing more exhaust gas pulses to turn the turbine faster and cause an increase in compressor output. When deck pressure is too great, the opposite occurs. The exhaust waste ticket fully opens and bypasses some of the exhaust gases to decrease exhaust flow across the turbine. An aftercooler is installed in the induction air path between the compressor stage and the air throttle inlet. Figure 3-20. Most turbochargers are capable of compressing the induction air to the point at which it can raise the air temperature by a factor of 5. This means that full power takeoff on a 100 degrees Fahrenheit day could produce induction air temperatures exiting the compressor at up to 500 degrees Fahrenheit. This would exceed the allowable throttle air inlet temperature on all reciprocating engine models. Typically, the maximum air throttle inlet temperature ranges from a low 230 degrees Fahrenheit to a high of 300 degrees Fahrenheit. Exceeding these maximums can place the combustion chambers closer to detonation. The function of the aftercooler is to cool the compressed air, which decreases the likelihood of detonation, and increases the charge air density, which improves the turbocharger performance for that engine design. On engine start, the controller senses insufficient compressor discharge pressure, deck pressure, and restricts the flow of oil from the engine intake, air filter, engine oil cooler. Induction, Y, cylinder 5, 3, 1. Injector nozzle shrouds. 6, 4, 2. Fuel pump, ambient air intake, alternate air source, pull to open. To fuel pressure gauge vent port check valve. Turbine, exhaust tailpipe, scavenge pump. To engine case, compressor, exhaust bypass, throttle control, throttle connected variable controller. To engine sump, engine exhaust, one-way check valve, tank vent, sump tank, waste ticket, actuator, vent overboard, bellows. Figure 3-19. Components of a turbocharger system engine. 3-15. Air reference lines, slip controller, aftercooler, induction Y, turbocharger, scavenge oil return. Figure 3-20. An aftercooler installation, waste ticket actuator to the engine. This causes the waste ticket butterfly valve to close. As the throttle is advanced, exhaust gas flows across the turbine increases, thereby increasing turbine/compressor shaft speed and compressor discharge pressure. The controller senses the difference between upper deck and manifold pressure. If either deck pressure or throttle differential pressure rises, the controller pipette valve opens, relieving oil pressure to the waste ticket actuator. This decreases turbocharger compressor discharge pressure, deck pressure. Variable absolute pressure controller. VAPC. The VAPC contains an oil control valve similar to the other controllers that were discussed. Figure 3-21. The oil restrictor is actuated by an aneroid bellows that is referenced to upper deck pressure. A cam connected to the throttle mechanism applies pressure to the restrictor valve and an aneroid. As the throttle is opened to greater values, the cam applies a greater pressure to the aneroid. This increases the amount of upper deck pressure necessary to compress the aneroid, and thereby open the oil restrictor valve. This means that the scheduled absolute value of upper deck pressure that is required to overcome the aneroid is variable by throttle position. As the throttle is opened wide, the manifold pressure and upper deck pressure requirements greatly increase. Slip controller. The slip controller is designed to maintain the rated compressor discharge pressure at wide open throttle, and to reduce this pressure at part throttle settings. Figure 3-22. A diaphragm, coupled with a spring-supported bellows for absolute pressure reference, is exposed to deck pressure and intake manifold pressure through ports located before and after the throttle, respectively. This arrangement constantly monitors deck pressure and the pressure differential between the deck and manifold pressure due to a partially closed throttle. If either deck pressure or throttle differential pressure rises, the controller pipette opens and decreases turbocharger discharge deck pressure. The slip controller is more sensitive to the throttle differential pressure than to deck pressure, thereby accomplishing deck pressure reduction as the throttle is closed. 3-16. Aneroid bellows assembly. Aneroid bellows assembly. Upper deck pressure. Manifold pressure sensing port. Diaphragm. Engine oil from waste ticket actuator. Oil restrictor valve. Dock pressure sensing port. Oil return to engine. Oil inlet port. Puppet seat. Oil drain port. Throttle controlled cam. Adjustment screw. Figure 3-21. A diagram of a variable absolute pressure controller. VAC. Figure 3-22. A diagram of a slipped controller used to maintain the rated compressor discharge pressure at wide open throttle. Absolute pressure controller. One device used to control the speed and output of the turbocharger, but controls the system only at maximum output, is the absolute pressure controller. The absolute pressure controller contains an aneroid bellows that is referenced to upper deck pressure. It operates the waste ticket, which diverts, more or less, exhaust gas over the turbine. As an absolute pressure setting is reached, it bypasses oil and relieves the pressure on the wastegate actuator. This allows the absolute pressure controller to control the maximum turbocharger compressor discharge pressure. The turbocharger is completely automatic, requiring no pilot action up to the critical altitude. Turbocharger system troubleshooting. Figure 3-23 includes some of the most common turbocharger system malfunctions together with their cause and repair. These troubleshooting procedures are presented as a guide only and should not be substituted for applicable manufacturer's instructions or troubleshooting procedures. Turbine engine inlet systems. The engine inlet of a turbine engine is designed to provide a relatively distortion-free flow of air, in the required quantity, to the inlet of the compressor. Figure 3-24. Many engines use inlet guide vanes, to help straighten the airflow and direct it into the first stages of the compressor. A uniform and steady airflow is necessary to avoid compressor stall. Airflow tends to stop or reverse direction of flow, and excessive internal engine temperatures in the turbine section. Normally, the air inlet duct is considered an airframe part, and not a part of the engine. However, the duct is very important to the engine's overall performance and the engine's ability to produce an optimum amount of thrust. A gas turbine engine consumes considerable more airflow than a reciprocating engine. The air entrance passage is correspondingly larger. Furthermore, it is more critical in determining engine and aircraft performance, especially at high airspeeds. Inefficiencies of the inlet duct result in successively magnified losses through other components of the engine. The inlet varies according to the type of turbine engine. Small turboprop and turboshaft engines have a lower airflow than large turbofan engines which require a completely different type of inlet. Many turboprop, auxiliary. 3-17. Trouble probable cause remedy. Aircraft fails to reach critical altitude. Engine surges. Wastegate will not close fully. Wastegate will not open. Differential controller malfunctions. Density controller malfunctions. Damaged compressor or turbine wheel exhaust system leaks faulty turbocharger bearings wastegate will not close fully malfunctioning controller bootstrapping wastegate malfunction controller malfunction wastegate bypass valve bearing tight oil inlet orifice blocked differential controller malfunction broken wastegate linkage oil outlet obstructed broken wastegate linkage controller malfunction seals leaking diaphragm broken controller valve stuck seals leaking bellows damaged valve stuck. Replace turbocharger repair leaks replace turbocharger refer to wastegate in the trouble column refer to differential controller in the trouble column ensure engine is operated in proper range refer to wastegate in the trouble column refer to differential controller in the trouble column replace bypass valve clean orifice refer to controller in the trouble column replace linkage and adjust wastegate for proper opening and closing clean and reconnect oil return line replace linkage and adjust wastegate opening and closing refer to controller in the trouble column replace controller replace controller replace controller replace controller replace controller replace controller. Figure 3-23. Common issues when troubleshooting turbocharger systems. Figure 3-24. An example of a turbine engine inlet. Power units and turboshaft engines use screens that cover the inlet to prevent foreign object damage. FOD. As aircraft speed increases, thrust tends to decrease somewhat. As the aircraft speed reaches a certain point, ram recovery compensates for the losses caused by the increases in speed. The inlet must be able to recover as much of the total pressure of the free airstream as possible. As air molecules are trapped and begin to be compressed in the inlet, much of the pressure loss is recovered. This added pressure at the inlet of the engine increases the pressure and airflow to the engine. This is known as ram recovery or total pressure recovery. The inlet duct must uniformly deliver air to the compressor inlet with as little turbulence and pressure variation as possible. The engine inlet duct must also hold the drag effect on the aircraft to a minimum. Air pressure drop in the engine inlet is caused by the friction of the air along both sides of the duct and by the bends in the duct system. Smooth flow depends upon keeping the amount of turbulence to a minimum as the air enters the duct. On engines with low flow rates, turning the airflow allows the engine notch to be smaller and have less drag. On turbofan engines, the duct must have a sufficiently straight section to ensure smooth, even airflow because of the high airflows. The choice of configuration of the entrance to the duct is dictated by the location of the engine within the aircraft and 3-18. The airspeed, altitude, and attitude at which the aircraft is designed to operate. Divided entrance duct. The requirements of high-speed, single or twin-engine military aircraft, in which the pilot sits low in the fuselage and close to the nose, render it difficult to employ the older type single-entrance duct, which is not used on modern aircraft. Some form of a divided duct, which takes air from either side of the fuselage, has become fairly widely used. This divided duct can be either a wing root inlet or a scoop at each side of the fuselage. Figure 3-25. Either type of duct presents more problems to the aircraft designer than a single-entrance duct because of the difficulty of obtaining sufficient air scoop area without imposing prohibitive amounts of drag. Internally, the problem is the same as that encountered with the single-entrance duct. To construct a duct of reasonable length with as few bends as possible, scoops at the sides of the fuselage are often used. These side scoops are placed as far forward as possible to permit a gradual bend toward the compressor inlet, making the airflow characteristics approach those of a single-entrance duct. A series of turning vanes is sometimes placed in the side scoop inlet to assist in straightening the incoming airflow and to prevent turbulence. Figure 3-25. An example of a divided entrance duct. Variable geometry duct. The main function of an inlet duct is to furnish the proper amount of air to the engine inlet. In a typical military aircraft using a turbojet or low-bypass turbofan engine, the maximum airflow requirements are such that the Mach number of the airflow directly ahead of the face of the engine is less than Mach 1. Airflow through the engine must be less than Mach 1 at all times. Therefore, under all flight conditions, the velocity of the airflow as it enters the air inlet duct must be reduced through the duct before the airflow is ready to enter the compressor. To accomplish this, inlet ducts are designed to function as diffusers, decreasing the velocity and increasing the static pressure of the air passing through them. Figure 3-26. Figure 3-26. An inlet duct acts as a diffuser to decrease the airflow velocity and to increase the static pressure of air. As with military supersonic aircraft, a diffuser progressively decreases in area in the downstream direction. Therefore, a supersonic inlet duct follows this general configuration until the velocity of the incoming air is reduced to Mach 1. The aft section of the duct then increases in area, since this part must act as a subsonic diffuser. Figure 3-27. In practice, inlet ducts for supersonic aircraft follows this general design only as much as practical, depending upon the design features of the aircraft. For very high-speed aircraft, the inside area of configuration of the duct is changed by a mechanical device as the speed of the aircraft increases or decreases. A duct of this type is usually known as a variable geometry inlet duct. Convergent supersonic section. Divergent subsonic section. Figure 3-27. The aft section of an inlet duct acting as a subsonic diffuser. Military aircraft use the three methods described above to diffuse the inlet air and slow the inlet airflow at supersonic flight speeds. One is to vary the area, or geometry, of the inlet duct either by using a movable restriction, such as a ramp or wedge, inside the duct. Another system is some sort of a 3-19 variable airflow bypass arrangement, which extracts part of the inlet airflow from the duct head of the engine. In some cases, a combination of both systems is used. The third method is the use of a shock wave in the airstream. A shock wave is a thin region of discontinuity in a flow of air or gas, during which the speed, pressure, density, and temperature of the air or gas undergo sudden change. Stronger shock waves produce larger changes in the properties of the air or gas. A shock wave is willfully set up in the supersonic flow of the air entering the duct by means of some restriction or small obstruction, which automatically protrudes into the duct at high flight Mach numbers. The shock wave results in diffusion of the airflow, which, in turn, decreases the velocity of the airflow. In at least one aircraft installation, both the shock method and the variable geometry method of causing diffusion are used in combination. The same device that changes the area of the duct also sets up a shock wave that further reduces the speed of the incoming air within the duct. The amount of change in duct area and the magnitude of the shock are varied automatically with the airspeed of the aircraft. Compressor inlet screens. To prevent the engine from readily ingesting any items that can be drawn in the intake, a compressor inlet screen is sometimes placed across the engine air inlet at some location along the inlet duct. Engines that incorporate inlet screens, such as turboprops, Figure 3-28, and APIS, Figure 3-29, are not as vulnerable to fault. The advantages and disadvantages of a screen vary. If the engine is readily subjected to internal damage, as would be the case for an engine having an axial compressor fitted with aluminum compressor blades, an inlet screen is almost a necessity. Screens, however, add appreciably to inlet duct pressure loss, and are very susceptible to icing. Failure due to fatigue is also a problem. A failed. Figure 3-29, an example of an inlet screen on an APU. Screen can sometimes cause more damage than no screen at all. In some instances, inlet screens are made retractable and may be withdrawn from the airstream after takeoff, or whenever icing conditions prevail. Such screens are subject to mechanical failure, and add both weight and bulk to the installation. In large turbofan engines having steel or titanium compressor fan blades, which do not damage easily, the disadvantages of compressor screens outweigh the advantages, so they are not generally used. Belmoth compressor inlets. A Belmoth inlet is usually installed on an engine undergoing testing in a test cell. Figure 3-30. It is generally equipped with probes that, with the use of instruments, can measure intake temperature and pressure, total and static. Figure 3-31. During testing, it is important that the outside static air is allowed to flow into the engine with as little resistance as possible. The bell is attached to the movable part of the test stand and moves with the engine. Figure 3-30. A bell inlet used during system tests. Figure 3-28. An example of a turboprop engine that incorporates inlet screens. 3-20.